Good evening, students. Now this is for elite, especially that is a writing part I have chosen, that's learning outcome 1. We can see that there are 3 parts to it. We can read it. The part number 1 is understand charge distribution on conductors and shells. State and justify the charges on the inner and outer surfaces of a spherical conducting shell, and we need to apply Gauss's law in scenarios with spherical symmetry. Explain why the electric field inside a solid metal sphere is 0 using Gauss's law. And also apply Gauss's law to derive expressions for electric fields and derive expression for electric field at a point outside a charged sphere using Gauss's law. So we'll take it separately, each section, and you can see they've given you the question numbers, page numbers, and also the question numbers from the PDF that had been shared with us. So first I'll explain and then we'll move on to the questions to solve so that you'll get a better understanding. Now, what is the first objective expecting you to learn is that you need to justify that the charges on the inner and outer surfaces of a spherical conducting shell. So what's the difference between a shell and a solid sphere? So shell will have the inside to be hollow, as you all know. So you have like a 2-layered, you should imagine this to be a 3-dimensional surface. So inside is hollow. So you have the charges distributed on this area only, right? Solid, you will have it. So solid, you can have 2 types. One, it could be a conductor. The other one could be an insulator or a non-conducting material. So both have to be treated differently because the charge distribution on a conductor is different from a charge distribution on an insulator. So to apply these, actually this differences and the way the charges are arranged should be understood well so that you apply it correctly in every situation. Alright, first let's see this one. Understand charge distribution on conductors and shells. State and justify the charges on inner and outer surfaces of a spherical conducting shell. You see here it's mentioned conducting shell. Now, see, if you take a solid conductor, we have the free electrons moving inside. So you will not have any charged particles or charged ions inside the solid, right? You will have it only on the surface, be it negative, be it positive. You'll have it on the surface of the solid, but inside it is neutral. So inside you don't find no charged particle you will find. Alright, so if you're choosing any Gaussian surface, what is the Gaussian rule? It is the Q net enclosed over epsilon naught. So if you are applying for a charged conductor, if you choose a Gaussian surface, inside if you do not have any charge enclosed, then it's the net field is going to be 0, or the flux is going to be 0 as well. Alright, but if it is an insulator, how does the charge get distributed? It will be uniform distribution. Right, so you'll have even distribution throughout in an insulator. This we have applied it even in a flat rectangular sheet where it is a conductor and non-conductor. For a conductor it is sigma over epsilon naught, and for insulator it was sigma over 2 epsilon naught. I hope you remember that. So that's about the arrangement of the charges in a conductor and insulator. So remember, inside a conductor it's like the shield. You don't have any charged particles inside. So the net electric field inside, or the net enclosed charges inside the solid conductor will be 0. But for insulator it will be different. Now, how do we apply this to a shell? So for the shell, so it's like you have, if it's a non-conducting medium or a non-conductor or an insulator, you will have the charges distributed uniformly. So you'll have it uniform distribution of the charges. Alright, so you don't have to be worried about if you have the surface charge, the volume charge density, you can find the total charge enclosed and so on. But this is for insulator. But your objective says for a conducting shell, how are the charges arranged? So we'll see that. Okay. So if you have a hollow shell, which is a conductor, okay, and if you have, say, inside, if it is negatively charged, okay, so that means there is a positively charged, so there's a positive charge in the middle to attract the negative charges, right? So imagine if there are 3 plus q charges in the middle of the conductor, so it will attract equivalent negative charges on the inner shell. Alright, so the inner shell will have equal and opposite charges to that of the one in the middle, opposite charges. Alright, so if you have plus 3q, you will have minus 3q on the inner shell of it. Now, sometimes in the question they give you the net charge, or the shell possesses, the shell is having a minus 5q charge in total. Alright, so what will be the outer shell's charge distribution? So already the negative 3q is pulled towards the inner surface, so the outer surface will have the remaining negative 2q. That's how it is distributed. So the middle, if you have 3q, equal and opposite charge will be assembled inside on the inner surface, and outer surface will be the extra negative charges, or if it's the other way around, that will be distributed. Okay, why is this distribution happening? Because you will find only on the surfaces the charges will be present in a conductor. Inside, as we saw before, inside the shell you will have 0 charge. That's the reason the electric field will be 0 as well as the flux will be 0 inside a conducting shell or a conducting solid sphere. So I hope that's clear. That's objective 1. Now what is objective 2? Apply Gauss's law in scenarios where with spherical symmetry. Explain why the net electric field inside, that's we have already seen, it's the same. So inside you do not have any net charge, hence the electric field is 0. So you can use this equation to prove your argument. Now the third one, apply Gauss's law to derive expressions for electric fields. Okay, this is the one which I told you in the beginning. Some students find it difficult, but if you go through step by step, slowly understand it and then apply, it will be easy. Derive the expression for the electric field at a point outside a charged sphere using Gauss's law. Now let's see all the cases when you have a spherical shell. Okay, so this is a picture of a spherical shell. Okay, so you have the inner radius to be R1, outer radius to be R2. Now see, inside the shell it is hollow, there is nothing, no charges present, so you have charges on the shell alone. So if you wish to find out the flux inside the shell where there is no charge here, see, this is a different case. We assume we were talking about charge distribution, but here there is no charge inside, so we have q net enclosed over epsilon naught. So since q net is 0, you have 0 flux. Okay, Newton meter square per coulomb. Alright, so inside the shell it is 0. How about outside the shell? How do you find? Outside the shell, as before, we need to start with which equation? The closed surface integral of the electric field times area will be equal to the Q net enclosed over epsilon naught. And remember, this area is for the area of the surface where the field is given off, and I've given you the math formulas and all that is required to remember for such situations. You will have it in the formula sheet, but you should know which formula to pick up and correctly apply it. So we are talking about outside the shell, right? So we choose a point, say R, outside the shell. Okay, we choose a Gaussian surface. So the Gaussian surface is also in a spherical form, which is enclosing the shell. Okay, I repeat, so the Gaussian surface is enclosing the shell, and the shell is having even charge distribution. Okay, so how do we find the Q net? You apply the formula of to find out rho times V, and you can apply it, and the area here will be 4 pi r square. Okay, so if you take A is constant, and if you integrate the total area, it'll be 4 pi r square equals Q enclosed over epsilon naught. So if I take E, I keep E alone here, so Q by 4 pi r square, so I bring this here, times epsilon naught. Now I can rearrange and write 4 pi epsilon naught times r square, and we know that 1 over 4 pi epsilon naught is K. So this becomes K Q over r square. And notice this is a general formula for, or the rule that we have been using for finding electric field at a point around a point charge. So for the shell, outside the shell, the formula is very similar to the previous equation, but the derivation should be clear if at all you're asked to prove it. Okay, so outside the shell we have this formula. So it's a hollow shell. Inside the hollow shell, the net electric flux is 0 because the charge is 0. Outside the shell, we have derived a formula which is similar to a point charge. Okay. Now let's see for a solid sphere. So for a solid sphere, okay, if you take a point, so inside and outside, so inside a solid sphere, now this has got what? Uniform charge distribution, so it's a insulator, uniform charge distribution. So that's our aim. So what are we trying to figure out? We are trying to find out an expression for the electric field by using Gaussian rule and the electric flux formula. So as before, we start with the same equation, that is E dot dA equals Q net or Q enclosed over epsilon naught. So inside, if you choose a point which is, say, R from here, so we choose a Gaussian surface with the radius r. Alright, so the Gaussian surface, we choose it with the radius r, and if you wish to find out the total charge enclosed, it should be Q times the volume. So what is the area that is enclosed in this? So it is the surface area for a sphere. So we take E outside and times it with the surface area for a sphere, which is 4 pi. We have taken this as r as radius. So this is the full radius of the solid sphere. You can take it as r1 just to differentiate it, or you can just leave it as r square, it's fine. So 4 pi r square is the surface area, which is equal to, now this is the Q enclosed. So Q enclosed inside this sphere, how do we find? You can find by using the uniform charge density, because we have uniform charge distribution here. So the charge density for a three-dimensional one will be rho. So if you multiply rho times V, you will get the Q enclosed. Now what's the volume of a sphere formula? Volume formula is 4 by 3 pi r cube. So remember, we are using two formulas for finding Q. The first formula is the charge density, the volume charge density multiplied by the volume will give you Q net or Q enclosed. So here the shape of the 3-dimension is a sphere. So we are using sphere's volume, so which is 4 by 3 pi r cube. Alright, so when you substitute it here, you get rho times 4 over 3 pi r cube. Now let's cancel the common terms, which are 4 pi. So 4 and pi get cancelled. You have r square with the 2 of the r, and you are left with r alone. So what's the final E that is there? Rho times r, sorry, I left out here. So this is over epsilon naught as well, right? So this entire thing is Q. This is Q, and we have epsilon naught here. Alright, so rho r over 3 epsilon naught will be the formula to find the electric field inside a solid sphere with uniform charge distribution. Alright, that's a derivation. Now for outside the solid sphere, so if you take a point outside the solid sphere, let's assume the distance again. Just to differentiate this, you can take it as r1. So this is as r at a point outside the sphere. So you will choose a Gaussian surface. Again, it's going to be in the shape of a sphere, okay, which is enclosing the entire solid inside. So you start with the same formula. The surface, the closed surface integral E times dA equals Q enclosed over epsilon naught. Now here E is constant. So if you take the integration of surface area, now here the surface area is the surface area of the sphere itself, which is 4 pi r square equals Q over epsilon naught. So E will be equal to Q over 4 pi r square times epsilon naught, which will again give you a very similar formula for KQ over r square. Okay, so if you notice this formula and outside a spherical shell, it's similar formulas you have as a point charge. Only for inside a solid sphere you get rho r over 3 epsilon naught. Okay, so this is a snapshot of all the 4 formulas inside the hollow region outside. This is there in the summary sheet, which I have already shared with you. So that's the whole derivation for that's learning outcome 2. Apply Gauss's law to find the spherical symmetry and to derive expressions for electric fields inside and outside. Right, now let's see the questions that's given in the PDF shared, and let's see what's the answer to each one of them is. Okay, now 13a, you have the solid metal sphere carries a charge of -2q. See, this is a hollow, the peach colored shell. This is a shell. Inside you have a solid metal sphere. It's a metal, and you have it has a charge of -2q. So it has got a negative charge of 2q, and the net charge on the spherical conducting shell is plus 3q. So the net charge on the shell is plus 3q, and the sphere is having -2q charge, and they ask you what's the charge on the inner and outer shell of hollow spherical conducting shell. So how do we approach this question? As I explained earlier, so when it has a negative q, an equal and opposite charge will be formed on the inner surface of the shell. So the inner surface should have a positive 2q charge. So the inner surface will be having a plus 2q charge to balance this negative 2q, the solid sphere which is kept in the middle. So equal and opposite charges will be attracted. So you will have all these charges assembled in the inner surface. So what is the outer surface then? How much will that be? So they give you the total shell, the charge accumulated in the shell is plus 3. So we have the inner surface plus 2q. So what will be the outer surface's charge? Outer surface will have 3q minus 2q, which will be 1q, or plus 1q, or just plus q. Charge will be on the outer surface. Okay, so inside is plus 2q, outside will be plus q. It's due to this concept. The part B, what's the electric field strength inside the solid metal sphere within the spherical conducting shell? So we have seen before, inside the solid it is a metal sphere. So metal is a conducting sphere, right? The conducting sphere inside the electric field is 0 because you don't have any net charge. Hence the part 1, E is 0, hence phi is equal to 0 as well. So you don't have charge because it is a conducting medium. Now for the second part also, within the spherical, again it is a conducting shell. Within the spherical, you will have on the surface the charges, but inside the spherical shell there will not be any charged particle you will find. The reason being the same, they will be neutral, hence again the phi inside will also be 0, or the electric field strength also will be 0. Okay, so these two scenarios you end up with 0 electric field. Now next question, uses Gauss's law to explain why the electric field strength inside the solid metal sphere is 0. So I already explained that. You can use the same argument. Last part of the question, use Gauss's law to explain why the electric field strength within the spherical conducting shell is 0. I think it's a repetition of the question, same argument you will place. The last part of the question is this, 13e. Find an expression for the magnitude of electric field E at a distance r from the center. So this is very similar to, this is a solid sphere, right? A solid sphere, and at a distance outside. So this is outside the solid, the same argument or the same similar equation. So you start with surface integral E dot dA equals q enclosed over epsilon naught. E times, so the area here is surface area, so which is 4 pi r square, which is q enclosed over epsilon naught. E will be equal to q enclosed over 4 pi, I write epsilon naught first and then times r square, so it is k times q enclosed over r square. Here you can write one more step because we know the q enclosed, which is negative 2q. It was already given to you in the question, so we can substitute that. So negative k 2q over r square, or negative 2kq over r square will be the electric field strength expression. So the final answer is E is equal to negative 2kq over r squared. Alright, so such questions, so you need to find out, this is like the dotted black circle is a Gaussian surface. So you choose a Gaussian surface and then apply the q enclosed formula. If it's a 2-dimension, you use sigma times area. If it's 3-dimension, you use rho times volume, and solve the questions. All the best.